Hello, welcome back to the channel. If you're new to this channel, we discuss the interesting things that we're doing in AI, higher ed benchmarking, machine learning, AI hardware, those kinds of topics in this channel, the things that we're doing at Perspective Data Science. So a big part of what we do at Perspective Data Science is higher ed benchmarking. If you're not sure what that is, it's basically selecting a peer set for a higher ed institution. So the example I'm going to give you is St. Xavier University, a university in Chicago. So what benchmarking is you find a set of schools to basically compare St. Xavier to. All right. And so typically what you want to do with benchmarking is select schools that are similar, some that are aspirational, and maybe some that are competitors for the same students. So that kind of idea. So there's a lot of decisions that need to be made in these benchmarking studies about like how to select peers, how many to select, and what criteria you use to select peers. And so that's going to be the focus of this video. I'm going to I get a lot of questions about how I select peer institutions for the schools I do benchmarking studies for. And I'm going to walk you through it. We use a really sort of scientific approach that's part of what's called a K nearest neighbor algorithm approach to select peers. And so I'll walk you through what that's all about. So just a bit about what our end tool looks like when we do select peers and start analyzing. I'll give you the example of St. Xavier here. This is the St. Xavier dashboard. So the first thing we do when we create these dashboards is to figure out what's the peer set that we're going to compare this school to. And you can see that typically I have a peer set in my dashboards of about 35 peer institutions. That number is a good number. The reason that I've chosen that number is that it's not too small and not too big, right? So there's issues if going both ways. If you go too small, you run the risk of having odd schools, outliers dominate the benchmarking analysis, and that's not good. Small sample problems with that. A big sample is great in that you get more precision in sort of identifying what's the normal discount rate, for example. Okay, what's a normal number of applications for a school like mine? It's great to get a really precise estimate of that. You need typically more than 10, peer institutions to sort of hone in on that estimate. But the downside of being too big is that you might be adding schools that are not really similar to the school that you're studying. So I found that 35 or so is usually a good sweet spot. Although there are some schools that are like very unique and it's hard to find 35, and you can't find 35. But I typically find most schools, there's at least 30 schools that are just like are really close. That would be a good comparison set. So what you're seeing here is St. Xavier University's peer set for one of our dashboards. And I'm going to show you how I came up with this peer set. Basically for when I come in and start doing benchmarking analysis, I don't know a whole lot about the school. So finding a peer set right out of the gate, you might sound difficult, but it's actually quite not really, right? We have a lot of data on these schools, and basically I let the data determine who the peers are, who's the most similar schools out there. And in that process, typically find schools that the target school, the school that we're studying might consider as aspirational, others that they would consider probably less prestigious, and you want both, all right? And for the reasons I'm about to discuss. So what I'm gonna show you in this video is how we generate this nearest neighbor algorithm distance measure, all right, to come up with the peer sets. And so you can see the result here and where they're located in the country. It actually turns out to be one of the variables that we have in the KNN algorithm to figure out, okay, some schools are really regional in focus. So we put in metrics of like how close other schools are to the same market. And so I'll walk you through all the variables that we use and the methodologies we use to sort of identify these peer institutions. All right. So what you can see here is that we get this distance measure showing how close, how similar other schools are to St. Xavier University. Of course, St. Xavier is as close as possible to itself, so the distance measure is 0, and then distance increases as schools get less similar. So what we do is we cut it off at some point. That's the K part of KNN. You pick a K. In this case, I don't know how many this is, but usually it's about 35 peers. I cut it off right there, and we keep that as the peer set. So you can see this gold highlighted schools are the peer set for this particular school, St. Xavier. All right, so let me walk you through how this works, some things to watch out for, and why I think it's the best way to go about finding peer institutions. All right, so here's the the overview of the discussion, and so I'll link this in the video. It's going to have also a demo, a really simple demo of how, with code, of how to do the KNN sort of calculation that we do to find peer institutions with Python code here at the bottom. There's a simple math equation here showing you the distance metric I just showed you, how that's actually calculated for a 3-dimensional calculation. We do it in many more dimensions than that, but and also allow for modifying the weights. But I'll show you how that all works with the detailed case with St. Xavier. Okay, so why do I do the KNN approach? It was really clear to me that there's an issue with how a lot of schools are selecting peer institutions, even for really sophisticated, expensive benchmarking studies. There's a tendency for schools to pick as their quote peers to sort of populate that group with almost all aspirational schools. I mean, by that I mean schools that the particular school that's under study would like to be like, but aren't necessarily like today. All right. So that's fine to have aspirational schools in a benchmarking study. I think it's great. It means you can see sort of where you might want to head in the future and how you might get there. But there's some big problems with having a benchmarking study populated by only aspirational schools, or predominantly aspirational schools. The problem is that every difference you find in your benchmarking study, like the main benefit of a benchmarking study is to find variables, outcomes, retention rates, spending, find any variable you can that we can measure and highlight if it's different from the peer set in some way. If it's quite a bit different, then you start asking questions. Why are we higher? Why are we lower? And so the problem with having a peer set that's all aspirational is a lot of times those schools are not very much like the school under study, or at least not today. A lot of times they have a lot more revenue, they have a lot more students, they have way higher demand for their products, essentially. They're more selective. And all of those things allow that school to be very different in the data as well. So, of course, then when you find differences in the data, it's really easy to dismiss those differences, saying, well, school X spends more on instruction because they have a lot more revenue, right? Really easy to just dismiss that and sort of forget about it, right? It's maybe valuable to know that, okay, to get to that level, you're going to need to spend more on research, more on instruction. They might have a higher retention rate, all of these things that go along with sort of moving up the rankings of higher ed. So the big problem with populating your benchmarking with just those kinds of schools is that it's easy to say, oh, shucks, we're not like them. We can't be like them right now, but we're going to try to get there, right? And you just kind of, the study's not very useful in that sense, because it's really easy to dismiss any differences that you find. All right, for good reason. A lot of you just don't have the resources. So one thing I've noticed doing these benchmarking studies is that comparing to aspirational schools is not usually even as useful to comparing to schools that you consider less prestigious or lower ranked than your school or whatever the target school is. The reason is you can't really dismiss differences in that case, right? For example, if you think, school X is not as good as your school, but school X has a better retention rate, that's really difficult to ignore, right? Like, why why are we ranked higher, or why do polls say that our school is better than school X, yet they have a better retention rate? Or why are students paying more to go to school X than they are going to our school, right? Like, why would that be the case if we're more prestigious? So these are really important questions that can't be just easily dismissed, especially when you think that you should have better metrics than school X. So that's really the benefit of benchmarking, right? Finding variables that don't look right, and start asking questions, all right? And it's really easy to sort of dismiss those questions as trivial when the schools are all aspirational, but it's not very easy to dismiss those. And in fact, you need to take them seriously, especially when you expect that your school is better than the school that you're finding has better outcomes, all right? Or at least financial outcomes, or whatever outcome you're looking at. So I think benchmarking studies are probably more useful when you compare your school to schools that you think are actual equivalent peers, or even lower ranked, less prestigious schools. I think it's even more useful to compare your school to those. Not because you want to get there, but it's really useful to find potential problems that you didn't know existed at your particular school. And then another issue with typical benchmarking studies that I've seen in my career is that there's just a tendency to pick too few comparison schools. Of course, the issue with too few comparison schools is that you've got outliers that will dominate the analysis for particular variables. You have just imprecision in general. The more schools you have, the less variability you're going to have in your sort of central tendency metric, be it mean, if you're looking at the average discount rate or the average retention rate. It's going to be less subject to outliers if you have a bigger sample. And so it's just generally better to have more to sort of combat that. Okay, so the fix that I found is to use a scientific approach. I use the part of the KNN algorithm, which is called K-nearest neighbors algorithm. That algorithm is typically used sort of like benchmarking, right? You find a peer set, a peer set of size K, called the nearest neighbors, and then you use that algorithm to predict what a particular school, in this particular case, would be sort of for retention and discount rate and whatever variable you're looking at, based on the average of the peer set. So that's one way to actually do benchmarking, just use straight up KNN. And a lot of benchmarking studies are like that. Mine aren't. We're more sophisticated than that. We use the peer set selected by the KNN, but we don't just look at the mean, we look at conditional means, really. It's regression analysis inside that peer set that we use to isolate, so what's the normal spending for a school of the target school size in this peer set. It's a little bit more sophisticated, a lot more sophisticated actually than looking at just the mean in the peer set. All right, so we use part of the KNN algorithm. In particular, we use the part that's calculating the peer set. And the way that the peer set is calculated in KNN is really simple, actually. You just calculate the distance between the target school and other schools on a number of metrics. And whichever schools have the closest distance, you keep those, right? So the top 30 closest schools, if your K is 30, you'd be picking the closest 30 peers as your KNN peer set. Like I said, I normally pick 35 or so to find for the peer set. Almost all of the benchmarking studies I do are 35. So basically what I'm doing is calculating the distance between the target school, St. Xavier in the case that I showed you, and all of the other schools that exist in the United States, and then selecting the 35 closest on that distance metric. All right, so that's the intuition. How do we calculate the distance? Well, it's pretty simple, actually. This is the distance metric. It's called Euclidean distance. This is the distance metric if you had 3 variables, right? In reality, I have far more than that, and I'll show you exactly how many I have typically. Lots of different characteristics of the schools, a lot more than 3, of course. And I'm going to show you a demo where you just have 2. It's really easy to break it down with 2 and visualize what's happening. But this is what it looks like if you have 3. So for example, if the variable x here were number of students, all right, and to find the distance between school 2 and school 1, you simply subtract, find the difference between the number of students between the schools, square it, and you've got this term part of the Euclidean distance. If variable y is revenue, you take school 2's revenue, subtract school 1's revenue, square it to get the squared difference between the 2 schools in terms of their revenue. And so on. If we had another variable here like Carnegie classification, actually it would be an indicator variable for the Carnegie classification. That's one of the variables I use. If they're the same Carnegie classification, this would be 0, squared would be 0. But if they're different Carnegie classification, it would be a 1 or -1, in which case you get a 1 for this term, so the distance increases. There's a little bit more to it than that because we do standardizing of the features, which it's really important in this case, but I'll show you how that works out so it can actually be 0s and 1s. But that's the idea. And then you just simply add up those terms and take the square root, and that's the distance. You're just simply getting the distance between the points in an n-dimensional space, okay? I'm gonna show you the 2-dimensional space with a simple code demo, and then walk you through some of the real world, how this is implemented in the real world with a lot more schools, thousands of schools, and dozens of dimensions on the school characteristics. But once you have an idea of how it works with just a few schools and 2 characteristics, it's really easy to see how this would be. You can generalize this code I'm about to walk you through to any dimension you want and to thousands of schools, no problem. All right, and so I'll show you how this works. All right, so let's jump into this demo. Okay, so what am I doing in this demo? Let me run this first part of the code here. All this is doing is loading, this is Python code, it's loading 2 packages. One is called NumPy, one is called Pandas. Those are really the sort of standard data analytics packages that you use for almost every project in Python. And what I'm doing is just creating a fake data set here. And this data set's gonna have, well, let's make the data set and I'll show you. All right. In Python, it's called a data frame. But this is what it looks like. Make this a little bit bigger, sorry. There we go. I think you can see it pretty well. Okay, so we just have a data set that has 3 columns here. The school name, all right, and this is just fake data. So my school is the one that I'm studying, okay? That's the target school of the benchmarking study. And then we have all these other schools, A, B, C, D, E, F. All right, those are just fake schools. And each of these schools has lots of characteristics, but just for simplicity, we're gonna have 2 characteristics in here that have number of students and their revenue in millions of dollars. So this is what it looks like. This is what actually the real data set looks like for me, pretty close, although we have thousands of schools and lots of, going horizontally here in the data set, we have lots of characteristics. All right, different types of students, full-time, part-time, graduate, undergrad, professional, yeah, lots of different characteristics here of the schools that go into this algorithm, but we're just gonna look at 2 here. So the key question, the key problem that we have is, how can we use this data to guide us to the most similar schools on these dimensions? Now, just looking at the data here, it's not clear, and especially if you had 1,000 schools, right? Just on 2 dimensions, it's kind of difficult to tell like which schools are the most similar. So we use Euclidean distance to calculate how similar the schools are. That's really all there is to it. All right, so let me walk you through how that works by going to the next lines of code here. All right, one thing we need to do for Euclidean distance is, you probably already saw this, but if you look at the, this is a really important point. I'll make sure I hit it right away. You look at how this distance metric is calculated. You're looking at squared differences between the one school's value of students versus the others, or this could be revenue, and difference in revenue squared. So a really important thing to keep in mind here is that if this is like revenue in millions of dollars, So you have a $20 million difference here, then you square that. This term is going to be massive, right? And it will like dominate the distance metric in that sense, because of course you don't have millions of students. The difference in students might be 1,000, difference in revenue might be hundreds of millions, right? And so if you didn't sort of standardize the scale of all of the variables in this distance metric, the variables that have the biggest scale are going to dominate the distance metric, right? To the extent that it would really just boil down to who had the most revenue, basically, all right, or the most similar revenue. So to counteract that, all we have to do is put all of the x's, all of the variables on the same scale. And the way that that's typically done is by standardizing them. All right, you just take, so for example, for students, that's what I'm doing here. I'm just creating a standardized data set that converts these numbers into differences from the mean, right? So the scale of all of the variables are going to be the same. They're just going to be measuring how far away that variable is from the mean in terms of the number of standard deviations. So if it's 1, that means that particular school's number of students was 1 standard deviation higher than the mean, all right? And same for revenue. If it's 1, it's again 1 standard deviation above the mean. So they're all on the same scale when you standardize, and that's really important so that no one variable dominates the distance metric just based on its scale. All right, they're all put on the same scale. So when we put them all on the same scale, the data frame will look a little bit different. So by the way, if you're not familiar with standardization, I just take the current value, the value that the school has, subtract the mean, and then divide that difference by the standard deviation. And in Python, it's really easy to do. This is the calculation. And I'm creating a new data set here called df_std. And it looks like this. All right. So all of these are now on the same scale. You see they're going to be numbers typically between -2 and 2, all on the same scale pretty much, just measuring how many standard deviations the particular school is away from the mean. In this particular case, this -0.74 means this is a smaller than average school. In fact, they're 3/4 of a standard deviation below the mean, all right? They're also about 3/4 of a standard deviation below the mean on revenue, all right? So this is a small, poorer school, school D. All right, or at least relative to average. All right, so rescaling is really important. I can't stress that enough. If you don't rescale, this is not going to be very useful. It's going to just sort of latch on to whichever school, whatever variable has the highest scale will typically dominate the distance metric, and it will just be basically which schools have the highest revenue or whatever variable has the highest scale. Or revenue would dominate the sort of finding of peers, which may not be bad, but I want it to be sort of spread out across a lot of variables that are important. Okay, so the next part here is to calculate the Euclidean distance. All right, so the first part is to create a function that just calculates that formula that I already showed you. Going back to, oops, that's not it. Going back to can't find it now. That's not even... Oh, here we go. Going back to this distance metric, I'm going to show you how to calculate this in code, right? Just basically take the current value, subtract off the other school's value, square it, add all these up, take the square root. All right, and that's what this function does here. All right, it's going to take the square root of a whole bunch of stuff, and as you guessed, it's going to take the reference school, which is the target school. I guess I changed the notation here, but the school that we're studying, my school, and subtracting off the school from some other school at a different row. So we're going to take like my school's students, for example, subtract students from school A. All right, square that. In Python, squaring is 2 stars and then a 2. And then take the square root of that, or sum it all up and then take the square root of that. All right, that's what the function is going to do. It's called Euclidean distance, and we'll call this actually down here when we apply it to our data set. The first thing I need to do, though, in order to run this function is I need to extract the reference school here. And so I do that. I extract this data. I'm going to run these 2 lines and show you what it's doing. So I just created a new object that's my target school. It's just taking the first row of data, the 0.078 students, and minus 0.16 revenue, and saving that. Basically, that's all it's doing. It's saving it in my school and saving it in this array like this. All right, these numbers. It's perfect. All right, I'm doing that so that I can inject that into the function that I just made. All right, so what we're going to do is apply that function to each row, including my own school row. And if it works right, we should get a distance of 0 for my school as well. So I'm going to go ahead and run that function row by row. That's essentially what's happening with this line of code. It happens really fast, of course, because this is all optimized. All right, this is Pandas running that, I think, in the background. I believe that's Pandas. All right, so here's what we get. And as expected, we get a distance of 0 for my school. That should happen, right? The difference between my school and my school is 0, right? They're exactly the same. So what this number is, though, is the difference between my school and school A, difference or distance between my school and school B and C, and so on. All right, so all I do now is, again, I want to pick some peers. I'm going to pick the closest peers in terms of distance, and that will be the peer set. So just showing you how that works again with code. Suppose I want to just sort this by distance and then keep the top 3 peers. That means I need to keep the top 4 rows because the first row is my school. So I'll keep the first 4 rows of data, and that's my nearest neighbor's data set. All right, and so here's my peer set that I could use for my benchmarking study. So I'm going to use, of course, my school, and then school A, D, and F. Those are the closest peers to my particular school. All right, so that's how it works. Really simple, of course. We pick 35 typically and roll with that and go ahead with our benchmarking. But just let me help you visualize what just happened. If we graph all the points at the beginning, so we have revenue on the vertical axis and number of students on the horizontal axis, you can see all of the points that we were looking at, right? In 2-dimensional space, it's really easy to visualize this Euclidean distance idea. So here's my school, and basically all I'm doing with Euclidean distance is finding the schools that are closest to my school as a bird would fly, right? Between point A and my school is pretty short. That's one of the peers. A and D, also pretty short. That's another peer. A and F, I think those are the peers that were selected. A, D, and F are the closest 3 schools to my school. We're selecting those as the peer schools. Now in the KNN algorithm, what that would do is take the average value of, say, retention or whatever for these 3 peers, whatever your peer set is, and say that's the predicted retention for my school, right? That's less sophisticated than what we do. Again, we try to control for the school's size in addition to doing the KNN algorithm. But one approach that's pretty powerful actually and used quite often is to just take the average in the peer set. Another approach is to do the average per student in the peer set. That's another way. It controls a little bit for the size of the school, but we do a little bit more sophisticated regression type analysis within the peer set. All right. I think that's it for the little demo. Let me show you how this is implemented in real. I'm gonna put, like I said, this will be linked in the description so you can see you have a full set of instructions here. If you're familiar with Python code, it'd be easy to modify this to work for your case. But let me show you my actual code. My actual code is actually not quite as clean as this version, but I'll show you. It's gone through lots of iterations of sort of trying to figure out which variables work the best to put into these. And I do a little bit less clean calculation of Euclidean distance because I use scikit-learn, but it's the same. All right, so let me show you an example of my code. I'm not going to run it in Python for you, but you can get an idea of what we're doing in this code. First part is just loading a bunch of data. All this data is from iPads. So we're loading the finance survey, the admission survey, the directory files, which has like all the IDs. What else is in there? I think there's Carnegie classification and that kind of stuff is in there as well. Enrollment, staffing, what kind of athletic programs they have. All of this data, we merge it all together. That's basically what's happening in the first several lines of code here. So we save all the financial aid variables, the enrollment variables, revenue variables, cost variables, admissions, put it all together. So we merge them all together here with these lines of code and sort it. Everything looks good. We drop some schools that have missing values, fill in some missing values. Pretty standard stuff for data analytics. All right, but what I really want to show you is the variables that we focus on in the KNN algorithm. All right, so these are the variables that we focus on. And this has just been sort of by experience what variables are most important. And the way that I've sort of gauged this is how close does the algorithm sort of match up with what people say are their peers, right? I know people are always great at selecting peer institutions, but on average, they're pretty good, right? So I really want the algorithm to be closely aligned with what administrators and other people say are their peer institutions, especially if the two institutions agree, right? So in IPEDS, most schools list their peer institutions. And so in particular, when two schools agree on that they're both peers, that's a pretty good indicator that that's a good peer set. So I've tried to fine tune this to sort of match how people view their peer sets, especially the ones that are in agreement. And these are the variables that seem to be most important and do the best at aligning. So the first four here, all about student body size. We have full-time equivalent undergrads, full-time equivalent grad students, full-time equivalent professional students, and full-time total, right? Adding all those up. All right, so these are like capturing a lot more than just the size of the school. So if a school has no professional students, it probably doesn't have graduate programs, right? Or maybe it's doctoral professional school if it's got a lot of these and not so many of the graduate student type. So there's a lot of information that's being picked up just in the makeup of the students and how big the student body is. The students per teacher also reveals a lot about the kind of style of the school. Is it like a intimate kind of classroom environment, small class sizes, or is it more like, you know, a stadium seating kind of thing? The Carnegie classification, of course, the entire purpose of those classifications is tried to sort of classify schools in different groups, and there's a lot of information revealed in there. The type of students that are attending is also quite important, right? Are the students attending, are they wealthy? Are they typically poorer? And you can pick that up a lot with the Pell Grant. Percentage of undergrads on Pell Grants are eligible for Pell Grants, percent of undergrads on federal student loans. And, you know, there are differences. Of course, there are all women's schools that I've studied. So that's important to have these percentage of women. And the way I do it now is actually different from what I have here. I have just an indicator for whether it's mostly women or not. Now I just use percentage of women at the school. And this has been useful for more than just revealing women's colleges and trying to pick out peers that are also women's colleges. It's also useful for picking out degree programs. I've noticed that schools that are like heavily engineering focused are also lower percentage of women attending those schools for whatever reason. But it's useful in sort of matching up the degree programs if they're pretty specialized in engineering, for example, or vice versa, if they're more like heavily medical or nursing or something like that. We also tend to see the opposite, right? More women in those schools. So we have a bunch of revenue characteristics here. What are the net tuition and fee revenue, athletics, auxiliary enterprise revenue, which is mostly housing athletics. It's going to reveal a lot about the structure of the school. Is it big time athletics? Is it residential or not? How big is the endowment? Of course, that matters quite a bit. A lot of schools with huge endowments, they get a lot of money for operations from their endowments. And then just total revenue, total expenses, just to sort of get us, make sure that we're in the same ballpark in terms of finances. And then this is within 250 miles. I do this more sophisticated now. I have actually distance between the target school as a bird would fly, and just using longitude and latitude, you can actually see the code up here. I actually use this miles variable now instead of within 250. It's kind of an arbitrary cutoff, so I use miles. This is an older dashboard that I've made improvements to the algorithm since. This is the St. Xavier dashboard. Okay, so what do I do next? Just collect all of these columns that I just saved here into a data frame called X. All right, those are the features I'm going to feed into the distance metric, and some of the variables are indicators like the Carnegie classification. You can't just, you could, but it's not ideal to enter them as just the numbers that they are. They don't really have a lot of meaning. So we have separate dummies for each category of the Carnegie classifications. So first create those dummies. And then you can see the really important step here. I'm standardizing all of the X's, right? Have a loop here that's going to standardize all of the X's. So again, they're all on the same scale. All right. And then I'm going to skip this for now and come back to it. Then basically I feed that X matrix into the KNN neighbors algorithm. I don't have it actually do the mean calculation though. I just want the distances, right? And so the key here is that I just extract the distances from the KNN algorithm. All right. And so the code for that is pretty straightforward here. It's scikit-learn's package to do KNN algorithm. I'm using the brute option here, which is the standard one where it's going to just calculate for all of the schools in my data. It's going to calculate the top 40 peers is what I've got it set at. So I pick k equals 40, but then I add 1 here. So it's fun. The reason for that is it does not include the school. How did that work again? I think it didn't include the school that, or it includes this. Yes, it includes the school, the target school in there. So if you just did 40, you would actually have 39 peers spit out by the algorithm because it includes itself as well. So if you do k plus 1, you'll get the school plus the other 40 peers spit out. Anyway, long story short, that's what it's spitting out. I'm saving those distances, right? That distance is that Euclidean distance. I don't use that function that I showed you. I probably should actually. It's going to be more efficient, but this runs really fast anyway. All right, and then I just keep those distances, create a data set, and put in a bunch of all the characteristics that went along with those peers, and then export it to be used in the dashboard. That's it. I save a file called kneighbors, and then that thing is sort of guiding the rest of the pages that go in the dashboard. All right, so I selected 40 here, but I actually, for the analysis, select only 35. This big K that you can't see in the background is imported from another sheet, and it's 35. Okay, so let me back up a little bit. This spits out a bunch of peers, all right? So remember in that distance metric, it's just going to weight all the variables the same, right? They're all on the same scale in terms of distances and standard deviations. They're all on the same scale. All right, once in a while, I like to compare, I always do this actually. I compare the 40 peers that get spit out, or the 35 that I keep, to the school's own statements of their peer set, right? And I usually like to do small fine tunings of the KNN just to make sure that it's including most, if not all of those peers that the school mentions, right? 35 is probably more than what the school mentions, but usually I can get most of them in just by making really small changes to the weights. All right, so that's a really simple thing to do here. Remember, we're standardizing all of these X's so that they have a mean of 0 and a standard deviation of 1. All right, one way to put more emphasis on a variable is just to scale it up, right? As I mentioned before. So I rescale some of these variables to give them more weight. That's basically what's happening here. So in the case of St. Xavier, it looks like I attached more weight to the Carnegie classification. The reason for that, of course, is that I wanted the peer set to be populated mostly, if not entirely, by schools that have the same Carnegie classification. All right. It probably didn't happen just automatically because I had to add more weight to the Carnegie classification variable. Same thing with the size of the student body. Wanted to make sure that the student, sometimes it will select peers that are on average bigger or smaller to sort of balance that out. You can attach more weight to the student body size, and that's what I did. And I wanted schools that had similar revenue structures. Perhaps the initial run without changing the weights had a lot of schools that were poorer or richer than St. Xavier. So I wanted to sort of balance that out and again, match up with what the school said its own peer set was. So there's small tweaks to these variables. By multiplying by 3, it basically means that the mean of the tuition and fee variable is going to be 0, but standard deviation will be 3. All right. So it's on a bigger scale, essentially. It's going to put more weight on, the tuition and fees. That's really it. Let me go back to my guide. If you're interested in knowing a lot more about this data or the code, I'm willing to share more than just showing you on the screen here. So just reach out in the comments, send me an email. You can email me through perspectivedatascience.com if you're interested in a lot more detail. But I will post the this code here for you to play around with, and this actually gets you really close to what you need to do. You just need to insert the IPEDS data essentially, and then you're off and running. And of course, modify the function so that it would accommodate an arbitrary number of, maybe I already do that. Yeah, I already do that. It's already going to accommodate as many features, variables as you put in it. So that's great. All right. Thanks for watching, and I'll see you next time.